I've now got to the stage where I've managed to solve this geometrical problem, but in a situation, I mean, so in a method that I don't totally like because it used trigonometry. I want to try to build on that trigonometrical argument and somehow sort of see if I can eliminate the trigonometry from it by sort of, so to speak, converting each step of the trigonometrical argument into a more geometrical argument and seeing if I can end up producing an exclusively geometrical argument. I'm not going to explain much about what I'm doing in this video. I'm going to assume if you're watching this that you've looked at the earlier ones, which is a big assumption given how long they've taken, but maybe you've looked at least at the end of the previous video, which I actually got to the end of the proof. Instead, I'm just going to just pretend this is just, in fact, it's at the time of recording, it's actually something like 2 weeks since I did the previous one. So it slipped out of my mind a little bit. And I also don't have all that much time to play with at the moment. So I'm not absolutely guaranteed to succeed in my endeavor in the time I've got, but we'll see how it goes. So let me, as usual, share my screen. And here is a diagram of something that I reduced the problem to. This I will re-explain, even though I explained quite a bit in the previous video. But here I've got I don't know what you call it, but a decoctagon or something like that. Anyway, so 18 gone, regular. And I've drawn it as a circle with 18 points sort of roughly evenly spaced around it. So I've got a point at the bottom, a point at the top, and then I've got this line, this horizontal chord here, joining sort of 3 round from the bottom and 3 round from the bottom in this way. And I've got a chord here from the center to the point just 1 to the left of the bottom. So sort of would be 7 o'clock, I suppose, except that we've got 18 points. So that would make it 10 o'clock in an 18-hour day or something. And we've got this other chord that goes from this point up to here. And the problem, it's not the problem as originally asked, but it was a reduction of the problem that I discovered and thought about in the second video of this series, and then solved in the third one, is to prove that these 3 lines intersect. So this chord here, and this radius, which can be extended to a diameter, which is a chord of sorts here, which seems to be a slightly non-obvious statement, and that it depends really in an important way on the fact we've got 18 points around here. And that was what the thing that I was finding a bit difficult to get my head around. So the way I ended up doing it was to say this length was L, and I would be a little bit careful about what I actually defined L to be. So L was from here to where this horizontal line intersected this diagonal line. And then M was the length from where this point here, the intersection of the vertical line with this horizontal chord, meets this line here. So not necessarily the same point, because this is an intersection of that, and this is an intersection of that and a different line. But we want to show that they are the same point, and I wanted to do that by showing that L plus M equals this length, and this length I can work out easily because this is an equilateral triangle, and this is an altitude of it, or looked at sideways. So for convenience, I took the radius of the circle to be 2, which meant that this length was √3, and then I did some trig, got an expression for L, an expression for M. Let's quickly have a look at what those were. I got that L was 8 sine 10 sine 100, and M was tan of 20. So I had this rather strange looking trig identity. Then I realized it was a bit silly to call that thing √3. It was better to stick with, I tried some stuff that didn't look very nice at all. Realized it was much nicer just to stick with calling it tan of 60, which is how it arose. So what is this thing where we have a 60-degree angle here, and so this thing here. That's if that's 1, that means that this must be tan of 60. Once I wrote it like that, so going back to here, so this became my equation. So how did I get that? That's because the one I started with had a tan of 20, which is I'd already simplified that to 4 sine 20 plus tan 20. So I then multiplied through by cos 20, I think. Is that what happened? 4. So I must have done some further simplification. 2 sine 40 plus sine 20. Oh, so I sort of did it from here. So if that I replace by tan 60, then I get this equation here, which after a couple of bits of manipulation ended up giving me what I wanted. So because the trig expressions I got were somewhat complicated, I think it's actually worth first having a look at this and seeing whether I can actually find a slightly simpler trigonometrical argument. And so, for example, maybe I don't want to look at L plus M equaling this length. Perhaps I just want to say that the length from here to where we meet this line should be the same as the length from here to where we meet this line. Can we do something like that? And it seems as though there may be a chance of that. So I'm going to draw a separate diagram and then draw in. So what I want to draw actually is just sort of this portion. Maybe I have to draw the whole thing. My problem is I've got to keep sort of jumping and well, I'll start with let's have a nice fresh page. So here's the center of the circle. I'll just draw that dotted line that we had before. That was the bottom point. And to get round a third of the way, no, that's a sixth of the way, so make an equilateral triangle there. And then I've got a kind of a point there and a point there. That looks reasonably realistic. And then I have a horizontal line like this. And I have, let me just quickly go and refresh my memory. So I've drawn in that horizontal. I certainly want to draw that line there. And then I want to draw this line, which I'm going to make not go through the same point, even though in fact it does. And then I want to put in a few extra lines to give me some triangles and things. And I need to get some angles. So what can I say? I know that that angle here is, because it's got 2 slices of the cake, is 40. And I also know that this angle here was 30. Let me just check that. That was the 30-degree angle that we want. So because this line here is parallel to this line, and this line makes an angle of 10 plus 20, so it's sort of halfway between here and here, plus another 20. So that line makes an angle of 30, so that makes an angle of 30. So that is indeed 30. And let me just put some more dotted lines in. So this dotted line makes an angle of 10. So this one, if I draw that, that's 30. and then that's 50, that exterior angle there, which means that that angle here is 50, which means that that angle here is 100. And we can draw a few more in. We've already established that that's parallel to that, and that was 30, so this one's 30. And so this one here, that angle is 110. I won't put it in down because I don't want to mess up the diagram too much. I think that'll probably do me for now. So what I want to prove is that this length here is the same as this length. So the length up to where this line crosses is the same as the length up to where this line crosses. Now that length, the longer one, I can use the sine rule with this 40 here, because I know that this length here, do I still want to call it 2, or should I just call it 1? Let's call the radius 1. I may regret that. Okay, so I know that 1 over sine 110 equals, so I'll call that length L, so it's different, and then that's up to here, and then M is the sort of longer one. I hope that's clear enough. L's from here to this point here, and M is this additional thing, except it's not actually additional. We're trying to prove that L equals M. So 1 over sine 110 equals L over sine 40. So that's that L equals sine 40 over sine 110. Sine 110 is the same as sine 70. Let's leave it like that for now, and let's think about what M is. Sorry, that was actually M. So I was applying the sine rule in this triangle, or was I? Yes, I did 1 over sine 110. Sorry, that's my mistake. M is that, and what's L? So L, I have to look at this little triangle here, and I had this length as my thing that I knew, which was, I think, 2 sine 10. Let me just check that. So I have a radius of 1. So here's the radius of 1, and then here's an angle of 10 up in there. And so that'll be sine of 10. Then I'll have another sine of 10 over here, so I'll have 2 sine of 10. So I have that 2 sine 10, that's the length of a side of the 18 gone, divided by sine of 30. That's this length divided by the sine of this angle equals L, this length, L over sine of 100. So that gives us that L equals 2 sine 10 times sine 100, which is the same as sine of 80, divided by sine of 30, but sine of 30 is a half. And therefore, that's actually dividing by a half, so we get 4 sine 10 sine 80. And now we get something even weirder than last time. Oh, might just check whether I can prove this. So we want 4 sine 10 sine 80. I think it's going to work out nicely, actually. Equals, times also sine 70 equals sine of 40. Now, what is sine 10 sine 80? Well, sine 80 is cos of 10. Beautiful, right. Actually, because I want to take this proof apart later, something nice seems to be happening here. So that equals 4 sine 10 cos 10 sine 70. So that's going to be easy geometrically. Is sine 40. And you can see something very nice is happening. So that 4 sine 10 cos 10 is just 2 sine 20. So we get 2 sine 20 sine 70 equals sine 40. Now exactly the same thing happens again. This is a cos 20, so that's 2 sine 20. This is much nicer than my previous trigonometrical proof. It gives me some hope of generalizing. And then that is just true by the rule for sine of 20 plus 20. Ooh, okay. So I did have to use the sine rule there, which is a bit, makes me a little bit worried. How do I convert that into a geometrical proof? Well, why don't we at least see if we can understand geometrically why 4 sine 10 sine 80 sine 70 equals sine 40. So I want somehow to draw. So basically it would help to have a drawing that tells me why sine 2 theta equals 2 sine theta cos theta. So let's try that. So I have theta and a theta, and this is going to be nice, I think. So let's extend that up to here. I have 1 there. So sine 2 theta is this length here. And that's sine 2 theta. Sine theta is that. So sine theta is this length here. If I want to multiply it by cos theta, then I'll have to drop a perpendicular here. And so this thing here seems to be sine theta cos theta. So I seem to want that twice that length here equals this length, which doesn't seem very true, because that's bigger than that, and that's bigger than that. So 2 of those don't seem to equal this. So I'm doing something very, very stupid somehow. Oh, yes, I see. This length is not sine theta. Okay, so it's because it's this length here is not 1, it's this that's 1. So let's just draw something that's actually correct for change. Get rid of all that. That's still sine 2 theta. So sine theta, that's more like it. So sine theta is going to be a 1, and then I'll have to drop a perpendicular onto that line there. So that's sine theta. And if I want to multiply that by cos theta, then I have to drop a perpendicular here. then I'll get that length there. That's sine theta cos theta. So why is that halfway between here and here? That's actually something I don't immediately see. That's funny. I would have thought this would have a really simple, I'm sure it does, but I'm just not seeing it. In itself, quite a nice geometrical problem. Because I've drawn it not terribly well, so it looks as though this is way under halfway, but this line didn't go completely straight. So I think that would be okay if I draw it better. I suppose I could do something horrible and sort of work out what this length is and so on. Well, maybe what I did here was I started by producing a sine 2 theta and then tried to show that it was equal to 2 sine theta cos theta. Maybe if I try it the other way around and just see if I can draw a picture that very naturally gives rise to 2 sine theta cos theta. Perhaps that will actually be better. So I'll try that. So here's my theta. How do I get a sine theta? Oops. I'll drop a perpendicular. So that's 1. That's sine theta. And now I drop a perpendicular. I think I can see this is going to work out much better. So if I drop a perpendicular here, then that's again theta. So this is sine theta cos theta. If I want 2 sine theta cos theta, I'll just go up the same direction, same amount in the other direction. So this total length here is 2 sine theta cos theta. And I think now comes the moment where I am forced to so I've got a 2 theta that naturally appears in this diagram. It's hard to resist the temptation to draw that in. I want to use it. But the trouble is I've got this 1 in the wrong place. And that is not a 1 here. And that's not a 1 here. If I want a 1, where do I go? Perhaps if I draw another theta here. And drop a perpendicular this way. So that now this length here is supposed to be the same as this length here, which is starting to look interestingly possible by some sort of symmetry or something, but I reflect in this line. I'm not going to send this point to here, so let's give up on that hope, simply because this line has a different length from this line, so that briefly felt as though it might do something. So why would this length be the same as this length? So that helped much. Quite surprisingly difficult to. Yet I feel I've seen very simple diagrams that do a more general thing of sine A plus B equals sine A cos B plus cos A sine B. So why am I having such trouble? Maybe I better try that. I'm wondering whether to go via e to the I A plus B, which of course gives me a proof. And see if I can convert that proof into a geometrical argument. Would that be a good idea? If I do that, e to the I beta plus 5 cos theta plus I sine theta. Equals cos theta cos 5 minus sine theta sine 5 plus blah blah blah. Theta should be sort of an inspiration somehow. Fine. And I want theta plus 5. So sine theta cos phi. Maybe this is going to help actually, because if I've got the two thetas equal, it sort of may lead me down wrong paths, whereas I've got fewer options. How can I create sine theta cos phi? That's not quite so easy. So here's a sine theta. I'm assuming the radius is 1, so that angle, length here is sine theta. If I multiply it by cos phi, I am actually rotating it around here, which is a bit strange. And then projecting it. So now that's how do I create a triangle? Well, this is the hypotenuse, and then it's got an angle of phi. To do it in some way that isn't horrible. But let me just do it in a way that is horrible. So there's sine theta cos phi. Cos theta is that length. And now multiplying by sine phi is going to be horrible. Well, if I can't even justify the addition rule for sine in a geometrical way, then there's not much hope of Okay, let me go back to this. We know that somehow it ought to involve rotation. So here's my sine theta. If I rotate it through phi, then I'll have a thing up here. But we'll go to here. So I've just rotated that little chord here, so it's just up here instead. And then what is sine theta cos phi? it's that length, and then this angle here will be, won't be phi. Oh, wait a minute, yes it will, because I've rotated this picture through phi. So by a nice piece of magic, this angle actually is phi, and so this length is sine theta cos phi. Now I hope that I'll be able to prove that this length will be sine phi cos theta, which I suppose I can do in a very similar way, that I'll take sine phi will be obtained by dropping a perpendicular from here to here. So that length is sine phi, but if I rotate it through theta, I'll end up with that length there. It would seem, but that's doing a little bit better than I wanted. That was sine phi. Oh yes, I just assumed that it was vertical, but there's no reason for it to be vertical. That is not vertical. What angle is it? What is this angle? This angle is actually just, it's making an angle of theta. We've got a phi here, it's making an angle of theta with the vertical. So when I rotate it through theta, I do get the vertical. So I seem to have proved a false addition law, namely that sine theta cos phi plus sine phi equals sine of theta plus phi. I haven't quite worked out where the cos theta is coming in. So this was a length of 1 here, a length of 1 here, a length of 1 here. That was sine of theta. I rotated it through by an angle of phi. So that's still sine of theta because I've just rotated it. But now it makes an angle of phi with the vertical, which means that this is sine theta times cos of phi. So that length there is sine theta times cos of phi. Now I take it's coming to me. So this length here is indeed sine of phi because that's 1 and that's phi. But when I rotate, I think that what I was accidentally assuming was that this bottom point will go to here. But in fact, it doesn't. There's no reason to suppose that it does. And in fact, not only is there no reason to suppose that it does, but it actually doesn't. So what? It will go somewhere beyond. And then we'll have to multiply by cos of theta to get to this point. So how do I actually work out what happens? I want to work out what happens if I rotate this point here through. What am I talking about? Said I rotate this through by theta. Oh, I think I finally know what I rotate this by 3 it will land on this line because this is an angle of theta. I still can't see my mistake. If I just draw in this auxiliary line, that's actually an angle of phi. Ah, so yeah, this thing here is an angle of phi, which means that oh, so I was doing something rather weird. It was this line here. That's not a chord. It, it's here, but then it goes down to some point there or something. A new diagram is called for. Theta. Phi. Ah. And all these three lengths are 1. We won't mark them in, they're all 1. I go around in a circle like that. I then take this length here and I draw in this angle or this line here, which makes an angle of theta here and phi here, so theta and phi the other way around. Now, if I rotate this round, it'll do something like that. Oops. And now that length is sine theta. That length is sine theta. And that angle is phi. And so that length is still sine theta. Cos phi. Now I want to do something. I basically want to do more or less exactly what I've done here, but just with phi instead. So I look at things from the perspective of phi. So what did I do to get the sine theta? I dropped a perpendicular to here. If I want to do to get a sine of phi, I just have to drop a perpendicular onto this one. That seems like a fair thing to do, is make it symmetrical. And so that length in this thing I've drawn rather faintly so as not to make too much of a mess. That's sine phi. If I now rotate that one through, I'll get to a point, I've rotated through theta, and this point is here, and I'm dropping a perpendicular onto that line. So that thing there is still sine phi. Actually, I wanted this length. I think that wasn't the right one to draw in. Let's get rid of some of this stuff. prove that this length here is cos theta sine phi, or sine phi cos theta. I know that that angle is, so there's something strange about that, because, at least on this diagram, because from here, I get sine of phi, because that angle is also phi. Oh no, but that's not one. The angle is sine of phi. Sorry, the length that is sine of phi is this. Let's put that in. That's something that's solidly sine of phi. So we see that it's just slightly bigger than the length we want, which is good because we want to multiply it by cos of a small angle. So how do I multiply by cos of a small angle? I just have to take a perpendicular. What am I saying? No, that'll be multiplied by cos of phi. Multiplied by cos of theta. So that's a bit. What I actually want to do is to prove that this thing here is a similar triangle to this, maybe, then that would give me that. I'd have an angle of theta here. Or anything on this line basically would be enough if I can find an angle of theta and a right angle. This would be the obvious point to aim for. So is that a right angle? I can't believe how unpleasant this is turning out to be. Especially given that the analytical proof is extremely straightforward. I'm going to take my cue from the complex numbers yet again. So I start with 1. This is e to the I theta equals cos theta plus I sine theta. And this is e to the I theta plus phi equals two different things. One is cos theta plus phi plus I sine theta plus phi, and the other is cos theta plus I sine theta cos phi plus I sine phi. And what we're really interested in is the y coordinate. That'll be my sine of theta plus phi. I want, so the y coordinate is given by the imaginary part. Why should the imaginary part? So where is this I? I'm building it up with a sort of I sine. There's a sine theta cos phi plus a cos theta sine phi. So where is my? I really want to look up this vertical line really. So can I find a sine theta cos phi length going up here? But actually, just what is this length? That's out of curiosity. It is this So let's start with it. So this length here is cos of theta plus phi. So this length here is going to be cos of theta plus phi times tan of theta. I don't think this is going to be very nice. Let's forget that. That's not really getting me anywhere. I'm going to have to stop in about 5 minutes. So I think it's going to be a dismal failure of a video. Apart from the beginning where I came up with that quite nice trig argument that was sort of prettier than what I started with, but my attempt to convert it into a geometrical argument has met with total failure for the moment. But because I'm stuck on something that is clearly well known and I ought to know, I'm sure I've even sort of seen pretty pictures in books that show exactly why the addition formula holds. I just seem to be having an off day and not being able to reconstruct those nice arguments. So what else could we could also, if I took that angle there, so that length there, that's sine theta. We want to go up by sine theta cos phi, so we don't want to go up by as much as sine theta. We draw, going back again, I'll sort of draw a thing that makes an angle phi with, it seemed to be sort of somewhat helpful last time, so that this angle's phi, so sine theta times cos of phi is we could do it like this. So I've made an angle of phi, so if I drop perpendicular here, then that length here is cos of phi. If I want that length to be multiplied by sine of theta, I have to drop another perpendicular here. I think this is actually the key that I've been missing. So that length there is sine theta cos phi. And then what length is going to be cos theta sine phi? Well, sine phi is that length. And to multiply that by cos theta, I have to drop a perpendicular again. That sounds a bit weird. What have I just done? Cos phi was that. And to multiply by sine, so cos phi was that, to multiply by sine theta. Drop a perpendicular onto that line. Now, cos of theta is that, a bit bigger. But I don't want to do that. The sine of phi was that length. And now to multiply that by cos theta, oh, yes, I actually have to drop, I think, that perpendicular. Is that the same line though? Is that angle theta? I took cos phi, yes, that angle was theta here. So cos phi sine theta is that, and sine phi cos theta is that. So what I want is that length plus that length equals weirdly that length. So can I say that something, that's really strange. Okay, I have to stop. That's very slightly irritating, but these things happen. I may carry on at some point.